In this video, we present a novel concept of a quadrotor UAV with tilting propellers. Standard quadrotors are limited in their mobility because of their intrinsic underactuation. They only have 4 independent control inputs versus their 6 degrees of freedom posed in space. The proposed quadrotor prototype, on the other hand, has the ability to also control the orientation of its 4 propellers, thus making it possible to overcome the aforementioned underactuation and behave as a fully actuated flying vehicle. This video will first present the hardware specifications of the recently developed prototype and then report the experimental results of first flight tests which show the capabilities of this new UAV concept. As first prototype developed by our group, we opted for a very low-cost solution with all parts available off the shelf. The overall costs, including all mechanical and electrical parts and actuators, are below 1,000 euros. The mechanical mainframe of the omnicopter is based on the microcopter concept, including the propellers, the brushless motors, and the brushless controllers. At the end of every arm of the omnicopter body, a rigidly connected axle allows rotation of the propeller group, containing the propeller motor and the servo motor for the tilting actuation. This servo motor has a maximum torque of 0.37 Newton-meter and a maximum rotation speed of 4.1 radians per second. The propeller group is designed so that its barycenter is as close as possible to the axle, as assumed by the dynamical model.
In this experiment, we address the case of a more complex trajectory following a lying H-shaped trajectory planar to the ground. While following this trajectory in position, the trajectory describes a sinusoidal rotation around the pitch axis. The main quantities of the trajectory are maximum velocity equals 0.2 meters per second, maximum acceleration equals 0.05 meters per second squared, maximum rotational angle equals 0.17 radian, and maximum rotational velocity equals 0.05 radians per second.
The position and orientation of the omnicopter are directly obtained from an external motion capture system at a frequency of 200 Hz. A marker tree consisting of 5 infrared markers is mounted on top of the omnicopter for this purpose. Knowing the position p, the linear velocity p dot is then obtained by a numerical differentiation, while the angular velocity of the main body is measured by an onboard IMU. This more advanced trajectory, we perform a takeoff, turn the desired orientation by 15 degrees, move the quadrotor linearly sideways, and then perform a rotation of 360 degrees around the z-axis of the main body while keeping the previously desired attitude.
In this last experiment, we show how the omnicopter is able to pass through a narrow passage among 2 obstacles with an inclined orientation, a maneuver that is clearly not possible with a standard quadrotor.